Okay, welcome everybody. I'll get started. Wanted to begin with just a couple of announcements again about the final exam and about the teacher course evaluation. So as a reminder, our final is on Tuesday of the week following Thanksgiving, Tuesday, December 1st. It'll be at 10:30 to 12:30. So it's not at our regular class time. It's at 10:30 to 12:30. And we'll meet on Zoom. I'll put a link to the Zoom final in Canvas. It will have the same format, same style of questions, problems as test 1 and test 2. So there'll be multiple choice questions, there'll be the numerical answer questions, and there'll be two fully worked out questions, two fully worked out problems where you'll upload your solutions, your written solutions for those problems. The material is cumulative and it's distributed evenly over the entire semester. So about 1/3 of the material will be on the material that was on test 1. About 1/3 of the exam will be on material from test 2, and about 1/3 from the remainder of the semester, post test 1 and post test 2. And right now I've got a old paper style practice test for you posted in Canvas, and I'll get a updated Canvas practice test for you posted in Canvas by Monday or Tuesday next week. Any questions on the final exam before I go on? Okay, if you have questions, feel free to put them in the chat. What lecture is this? Well, that's an interesting question. What lecture is this? It's, if you mean what number? I believe so. Yeah, there might have been a confusion over the numbers. It should be lecture 25. Originally, I had 26 lectures in this class, but we lost one lecture because of the election. And at that point, there was a mismatch between my numbering of lectures, I think. But there, I believe, posted in Canvas are lectures 1 through 25, and this is lecture 25. There will be a review, which is next week. That will be lecture, quote, lecture 26. Okay, one other reminder quickly is that to complete the teacher course evaluation, remember, once the class gets to 80% response on the teacher course evaluation, I'll credit you all 1% of your total score when that's completed. We're not there yet. We're about halfway. We're about 40% now. This printout I'm showing right now was from the beginning of the week, but I did look this morning, it was about 40%. Do we have homework due next Wednesday? That's actually a very good question. And what I think I'm going to do is, there is a homework assignment for next Wednesday, but I'm not going to count it towards your grade. I'm not going to count it towards your final score. So I don't want to discourage you doing that homework, because that material is potentially on the exam, on the test. No, I'm not going to give extra credit for it, but I will not count that towards, it will not be counted towards your homework grade. Okay, I think I'll move on with today's material. If you have other questions related to more organizational stuff related to the final or your scores so far, those sort of things. I can try and answer them at the end of the class. Or I've got a few emails today, and I'll try and get through answering those during the day today. So either way, let me know by email or let me know at the end of class. Right. Oh, do we have a recitation next week? So no, you don't have a recitation next week because the last day of classes is Tuesday and your recitation is on the Wednesday. So there is no recitation that covers the homework material from today's class. Okay, I'm now determined to get started with the actual class. So last class we talked about periodic motion. It was our first class on periodic motion, and we talked about a particular example of periodic motion, a mass spring system. This class, we're going to continue talking about periodic motion. It's our second class on periodic motion, and we're going to talk about another example of periodic motion. Is what we call a pendulum, what we often call actually a simple pendulum. So let me start by just a few remarks about the history of the pendulum and the importance of the pendulum, because it was actually an important topic in science. It was a sort of breakthrough topic in science. So the history is that Galileo actually came up with the idea of the pendulum and came up with the idea of the pendulum clock. So there's this sort of story about Galileo. I don't know whether it's a true story about Galileo or not a true story. But as you probably know, he was from Pisa, and he was in the cathedral in Pisa, and he noticed the lamps or the candelabras swinging to and fro in the cathedral in Pisa. And he noticed an interesting thing about the swinging to and fro of the candelabras or the lamps in this Pisa cathedral. And it was that the period of the oscillations of these candelabras or lamps was independent of the amplitude, the size of the oscillations. So it didn't seem to matter whether their swings to and fro were just very small swings to left and right or much larger swings to left and right. The period of the oscillations was the same, was independent of the amplitude. And of course, we don't know if somebody else had noticed that before Galileo had noticed it. But when he noticed that, he came up with the idea of using a pendulum as a clock for measuring time. And before using pendula as clocks for measuring time, people relied on natural repetitive motion, like the motion of the Earth around the sun, or the rotation of the Earth about its axis, or the motion of the moon around the Earth to measure time intervals. But now Galileo was suggesting a man-made way of measuring time intervals using the swinging, the oscillation to and fro of a pendulum, like a lamp on a cable, like a candelabra on a cable. It was later on that actually Isaac Newton and also Robert Hooke explained the physics of the pendulum motion, the periodic motion of the candelabra on the cable or the lamp on the cable as due to a linear restoring force. And that periodic motion, harmonic motion, is a sort of emergent phenomena from a linear restoring force. And actually, it was after that that an interesting point was made by a scientist, Huygens, a Dutch scientist, Huygens, who actually figured out that Galileo's observation that the the period of the pendulum was independent of the amplitude is true. The period of the pendulum is independent of the amplitude when the oscillations are relatively small. But if you have very large swings of a pendulum, very wide swings of a pendulum, very large angles of swings of a pendulum, then that independence of the period on the amplitude actually breaks down. In today's class, we're not going to worry about Huygens' point that it actually this independence of the period on the amplitude breaks down at very large amplitude oscillations. We're not going to worry about that. We're just going to think of it as a pendulum as having oscillations that are independent of the amplitude of the swings to and fro. Okay, there's several important things about the pendulum and several important reasons that the pendulum was a real breakthrough. So it was the point in human history when there became the first precise measurements of time, which actually facilitated navigation by ship or boat and facilitated the exploration of the world. So it had a huge effect on humankind. It was the first time we could really, using pendulums, measure accurately, precisely the acceleration of gravity. It was the most accurate way of measuring the acceleration of gravity. And it actually led to some really intriguing, interesting discoveries. One is the fact that, I don't know whether you know this or not, but the Earth has a bulge. The Earth is fatter around the equator than it is around the poles. And that was uncovered by measurements with pendulum. Of course, you also know that the Earth is rotating. We all know that the Earth is rotating, but the rotation was actually measured for the first time with pendulums. So pendulums, the understanding of pendulums, they're used for measuring times, they're used for measuring the acceleration of gravity. It was a very important breakthrough in science physics. Okay, let's talk about the theory of the pendulum. And to talk about the theory of the pendulum, I want to go back to the theory of the spring mass system. So both of those systems, the simple pendulum and the spring mass system, they both exhibit periodic motion. They both exhibit simple harmonic motion. And in both cases, that periodic simple harmonic motion is emergent from an underlying, a sort of foundation of a linear restoring force. So here's the case of the spring. I'm just going to get my pen working again. Here's the case of the spring and the mass spring pendulum. And at the core of it, at the heart of it, is this linear restoring force. So in my little picture here, I'm compressing the spring by pushing the mass upwards, and it pushes backwards with a force that's in proportion to the compression of the spring. And that's a linear restoring force. And that's the core, that's the heart of periodic motion. That's what you need. That's how simple harmonic motion emerges. And so this little equation up here gives rise to, sort of gives birth to periodic motion. Well, with that understanding, in the last class, we explored that periodic motion. And so upstairs on this slide, upstairs on the top left, here's an example of the periodic motion where we see the mass over here on the right with a stretched spring being pulled back towards the equilibrium point, passing through the equilibrium point, and then compressing the spring in the center here and being pushed back towards the equilibrium point, passing through the equilibrium point, and then stretching the spring and being compressed back. And so that's a picture of the simple harmonic motion that emerges from the linear restoring force. And over here on the right, I've actually quantified it by sketching out position versus time. It oscillates sinusoidally. Velocity versus time. It oscillates sinusoidally. Acceleration versus time. That also oscillates sinusoidally. Now, those oscillations of the mass on the spring have a characteristic frequency. They have a characteristic period that actually reflects the spring constant and reflects the mass. And we saw how that characteristic frequency emerged from the restoring force. So if you might remember in the last class, well, we wrote down that restoring force and we wrote down the corresponding acceleration. We just divided the restoring force by the mass of the object. When you write down the acceleration is proportional to the displacement. It's in the opposite direction to the displacement, and it has this numerical factor, the spring constant divided by the mass in that equation. And that factor is actually the characteristic frequency, the square of the characteristic frequency of the periodic motion. So it's that leads to periodic motion. Here's the expression of the sinusoidal motion. And here's the characteristic frequency. It goes as the square root of the spring constant divided by the mass. So that was a recap from last class. But now let's just apply those slides, apply those ideas to the simple pendulum. So the important thing with this simple pendulum is to realize that there's also a linear restoring force for this simple pendulum, which again is the core of the heart of the emergent harmonic motion. So over here on the right-hand side, I've drawn a simple pendulum. So this is what I mean by a simple pendulum. You see this string here, or this cable, or this wire, and this mass here. That's what we mean by a simple pendulum. It's just a thin string, thin wire, thin cable with a mass attached to the end of it. And of course, it's characterized by the mass of the mass and the length of the string. Now, that simple pendulum, if I displace it to the right of the vertical, so here's displaced to the right of the vertical, or I could have displaced it to the left of the vertical if I put it over here on the left. It experiences a restoring force. It experiences a restoring force due to gravity. So gravity is pulling the pendulum downwards. But a component of gravity, a piece of that gravitational force, acts in the direction of the pendulum's swing. It's a relatively small piece. It'll be W sine theta, just like an incline, where theta is this angle of the string with respect to the vertical. So the first thing to realize is that there is a restoring force for a mass on a string, just like there was a restoring force for a mass on a spring. In the mass on the spring, we're more obviously stretching or compressing the spring. In the mass on the string, our restoring force is that portion of gravity that acts in the direction that the mass on the string can swing. And it's W sine theta. Okay, so there's the restoring force. Now, if this angle is small, if this angle theta is small, so maybe it's like 1 degree or 2 degrees or 3 or 4 or 5 degrees, something rather small compared to 90 degrees. Then there's an interesting approximation that angle in radians, if you measure that angle theta in radians, it's equal to this ratio here, x over L. X is the distance of the mass from the equilibrium point, this vertical line here. So that's x, and L is the length of the string. And so this is called a small angle approximation. All we need to worry about here is that for small oscillations, that restoring force, firstly that angle theta is in proportion to the displacement x, and actually the restoring force is also simply in proportion to this distance x. So for example, if x was 0, there's no restoring force. As you increase x, as you pull the pendulum more towards the right, the restoring force gets correspondingly bigger. If you were to pull the pendulum towards the left, the restoring force would get correspondingly bigger. And so actually for small oscillations, there's a linear restoring force. Just like the spring force depended on the displacement of the spring from equilibrium, how much you stretched it or compressed it from equilibrium, the restoring force for the simple pendulum depends on how much you pulled the pendulum towards the left and right, away from the vertical. They're both in proportion to x. They're both in proportion to the displacement of the mass. And so that's the core, that's the heart of periodic motion for the pendulum, that there is also a restoring force there. That actually means that all that machinery, all that mathematics, all those arguments that we made for the mass spring system, we can make the same arguments, do the same machinery, do the same mathematics for the pendulum arrangement. So here's on the left-hand side in this sketch, I just replaced the spring oscillating, or the mass oscillating to and fro on the spring, with the pendulum oscillating to and fro about the equilibrium. So here it is on the right, it's being pulled back by the restoring force, passes through the equilibrium, swings over to the left, it's being pulled back by the restoring force, swings through the equilibrium point. Now it's over here on the right again, it's going to be pulled back towards the left through the equilibrium point. And that's the restoring force at work. And that restoring force creates the sinusoidal, or the periodic or the harmonic motion. So here would be position versus time, this sinusoidal curve, velocity versus time. It also obeys this sinusoidal curve. Acceleration of the mass on the string also obeys this sinusoidal curve. They all emerge from this linear restoring force. Like we did for the mass spring system, we wrote down an equation for the acceleration, and we saw that the coefficient in that equation for the acceleration, which depended there on the spring constant and the object's mass, govern the characteristic frequency of the oscillations. Likewise here, we can write down an equation for the acceleration of the mass on the string in terms of the displacement of the mass from the equilibrium point. And again here, we'll see that there's a coefficient that determines the relationship between the acceleration and the displacement. And again, that coefficient corresponds to the square of the characteristic frequency of, this time, not the mass spring system, but the simple pendulum system. So that's what I did here. Upstairs in red here, this is the linear restoring force. I divided by the mass. Actually, that canceled out a mass. And I get this equation for the acceleration as a function of displacement. Again, the acceleration is in proportion to the displacement. It's opposite to the direction of the displacement. It has this coefficient, which is acceleration of gravity over the length of the string. And that, again, is the square of the characteristic frequency of this sinusoidal motion. So then you can write down the harmonic motion, that x, for example, or v or a, they all vary sinusoidally, and the characteristic frequency of those sinusoidal oscillations, omega, is determined by the square root of this coefficient. It's the square root not of spring constant divided by mass, it's the square root of acceleration of gravity divided by length of pendulum. And that's the theory of the pendulum. And that's all, in a sense, a little bit of history going back, to, as I say, to the days of those guys we've met before. Robert Hooke, he's one of my favorite scientists, and Isaac Newton, you know, one of the most important scientists ever. Okay, I want to show you a couple of demonstrations of the pendulum and how its oscillations don't depend on amplitude, and do, for example, depend on the length of the string. A lot of this work was first done by this scientist, Christian Huygens, that I mentioned. He was the person that built the first accurate pendulum clocks. And so we're sort of repeating some of his studies as we look at these demonstrations. So I'm going to share a different screen here. Okay, so I hope you can see a screen. Let me just stop this for a moment. So I went in the chemistry, physics, large lecture room, and I hooked up this cable to the ceiling, and I had a bowling ball at home, and I brought the bowling ball in, and I've connected it to the cable that's attached to the ceiling. I've made a simple pendulum. I was quite proud of myself. And so the simple pendulum is a long cable with a bowling ball attached. And we're just going to look at the motion of the simple pendulum. And I'm going to show you the motion of the simple pendulum when it swings to and fro with several different amplitudes. I'll start with the largest one, and I'll work my way to the smallest amplitude. And as we look at the swinging to and fro, the large amplitude, intermediate amplitude, small amplitude, I'd encourage you to think about the period and to try and in your head, right? It's not easy, but compare the period. Does the period change? And in that way, you'll be doing what Galileo did. That's what he thought about when he looked at the lamp swinging to and fro in Pisa Cathedral. We couldn't go to Pisa. I couldn't get permission to swing the lamps to and fro, so we're doing the bowling ball case. So just think about that period there. Just try and remember that length of time in your short-term memory or whatever. I don't know how you really remember time intervals, but we're going to have to try and remember that time interval. Because now I'm going to decrease the amplitude. I'm going to decrease it by a factor of 2. And now think about the time interval now. Now look, it's obvious that the pendulum is not traveling as far. It's only swinging half the distance, only swinging through half the size of the arcs that it was swinging in the first case. But it's also going, it's clear, it's going considerably slower as it swings to and fro. And I think you believe that it was actually the same duration of time for one complete swing. Now I'm going to do it with another swing that's half again the size. And you see again, right, the pendulum is swinging to and fro even slower. But the duration of one complete swing has actually stayed the same. And that's it. Okay, that was the first movie. So that I hope that movie or video. That movie or video is we're doing what Galileo did. We're noticing what Galileo noticed, that the amplitude of the swing is independent of the the period is independent of the amplitude, and we're getting the idea we could use a pendulum as a clock. Now I've got two pendulums in this video, a shorter one and a longer one, and we're comparing the periods of these two pendula. And if you notice, it's there's something traumatic about watching this one, I think. But if you notice, the periods are different. The shorter one seems to catch up with the longer one and then get ahead of the longer one. The shorter one had a shorter period. The longer one had a longer period. I'm now going to add some extra mass to the shorter one and the longer one. Actually, I'm doubling the masses of the original two masses. And now I'm going to swing again the pendulum to and fro. But there's a couple of things to notice here. One is that adding the mass has not changed the frequencies that the pendulum swing to and fro at. They're still swinging to and fro with the same frequencies. But it's still true that the shorter one is, its period is shorter. The longer one, its period is longer. So the shorter one again caught up with the longer one and sped past the longer one. And now I'm actually going to triple the masses on the pendulum. I'm putting an extra mass on the pendulum that is double the original mass. So that's going to triple the masses and get them swinging again. And again, that makes no difference. The mass is making no difference to the period of the pendulum. It's just that the length of string that makes the difference to the period of the pendulum. The shorter one has the shorter period, the longer one, the longer period. The shorter one catches up with the oscillations of the longer one and goes past the oscillations of the longer one. Okay, I'm going to go back to my slides now. I just noticed from Isabel, there's a question in the chat, which is an interesting question, actually, so I want to answer that. I gave several equations for the restoring force for the pendulum. So one was W sine theta, or mg sine theta. That one's exactly correct. I then gave formulas in this small angle approximation, Wx over L or mgx over L. That's an approximation. Now that's the approximate well we're going to be working in. And that's the approximate well where there's a linear restoring force and where we get this simple harmonic motion. So that was a great question. That's an important point. I just want to remark on energy, and I'm going to talk a little bit about energy in periodic motion again. So in the prior class, we talked about energy in periodic motion for the mass on the spring. And now I'm going to mention energy in periodic motion for the mass on the string or the pendulum. So look, here in the middle, this is the mass on the spring. So this is something from last class. We've got the spring to the right of the equilibrium point, passing through the equilibrium point, reaching the left of the equilibrium point, passing back through the equilibrium, going to the right of the equilibrium. And we got the pendulum doing exactly the same pattern. Starts over here on the right of the equilibrium point, passes through the equilibrium, moves to over here on the left of the equilibrium point, is pulled back through the equilibrium, And then finally, it ends up over here on the right at the equilibrium point. Now, the nature of the restoring forces, the origins of the restoring forces are very different. One's due to gravity and one's due to a spring. But the pattern emerging from the linear restoring forces is identical in these two cases. And so is the pattern of energy and transfer and flow of energy in the mass spring oscillation and in the simple pendulum oscillations. And that's this picture, this bar graph plot I put over here on the far right. So there's three different colored bars on this plot. There's red. And red represents the total energy of either the spring mass system or the string mass system. So it's the total energy. And in both cases, that total energy in general is some combination of kinetic energy, because you typically got something moving, and some combination of potential energy, because you got some form of potential energy like gravitational spring potential energy. Now, what you see here is that the total energy, the red bar, that remains the same all the time. It just doesn't change. What you see changing are the individual bands of energy. You see the kinetic energy and the potential energy, they change. They actually oscillate to and fro out of what we would say out of phase with one another, out of sync with one another. So for example, let's take a look at the kinetic energy. The kinetic energy is biggest when you travel through the equilibrium point. That's here and here for the pendulum. That's here and here for the spring system. And that's when the kinetic energy is maximum. It's 100% of the energy. And there's actually no potential energy when you're at the equilibrium point. And vice versa, when you're on the far right or you're on the far left for the mass string system, pendulum system, or far right or far left for the mass spring system, those are the cases where the spring is most compressed, or the gravitational potential energy is largest. That's where the potential energy is highest, here and here. And you've got no kinetic energy. And so you see here that the total energy remains constant, but the two different bands of energy, the kinetic energy and the, what's the other one? Potential energy, they oscillate to and fro. Just think of a seesaw. And on one end is kinetic energy and one end is potential energy. If I'd name my kids like kinetic energy and potential energy, and they got on a seesaw, they swing up and down and up and down. That's the oscillation between kinetic energy and potential energy. But in total, their total energy is constant. Let's look at an example of energy. Now, I could have done a pendulum example, or I could have done a spring example, because we've just seen that the oscillations of the energy are really the same oscillations between kinetic potential energy in the mass spring system and the pendulum system. So actually, I'm going to do the a mass spring system as an example of energy concepts for periodic motion, but we could have equally well have done a pendulum situation for an example of energy concepts in a periodic motion. So just take a look for a moment at this little diagram. It's again the spring, mass on the spring oscillating to and fro over here on the right, on the left, and then here's a picture of the energy over here on the right. And I've added to that picture a couple of equations. This is the maximum potential energy. It's 1/2 Ka squared. A is the maximum displacement. It's the amplitude of the oscillations. And here's the maximum kinetic energy. It occurs when the mass swings through the equilibrium point. It's 1/2 mv squared, where v is the maximum velocity that you get at the equilibrium point. And we're going to use those equations as we look at an example on the next slide of total energy and kinetic and potential energy and energy conservation for harmonic motion. Okay, so in this question, it says we got a mass on a spring. We're told the mass is 0.4 kilograms. We're told the spring constant is 19.6 Newton meters. We're told that the mass in the spring arranged horizontally on a frictionless table. And we told that we initially displaced the mass from the equilibrium point, i.e. we compressed the spring from the equilibrium point by 4 centimeters. And then we're going to release it. And knowing that initial condition that we compressed the spring by an amount of 4 centimeters and we release the object from rest, we're going to use energy concepts, energy conservation, to find the speed of the object. We're going to find its maximum speed, and we're going to find its speed when the spring is either compressed or stretched 1.5 centimeters. So firstly, the maximum speed. That's what I've done on this slide. Here we're going to work out maximum speed. And we're going to work it out using energy concepts. So the first thing I did, of course, was draw a picture. That's upstairs here. Here's a spring. I actually drew it as stretched. It's stretched by an amount of 4 centimeters, 0.04 meters. The mass was 0.4 kilograms, and the spring constant is 90.6 Newton meters. So that's the information I was given. The basic concept here is that there's a total amount of energy in that situation because of the stretching of the spring. Once we release the mass on the spring, the mass will move, the spring will stretch and compress, but the total energy stays the same. And if we were to compare the maximum kinetic energy, the maximum potential energy, those energies would be the same. They're at different instants in time, different moments in time, but the maximum kinetic energy is equal to the maximum potential energy. That's equal to the total energy of the mass spring system. So that's our basic starting idea. So I started with that, and I filled in that expression for the maximum kinetic energy. I filled in that expression for the maximum potential energy. So the maximum potential energy is when the spring is most stretched. It's a distance of its amplitude, the amplitude of the oscillations from the equilibrium point. The maximum kinetic energy is when the spring is passing through the equilibrium point. That's when you get the maximum velocity. But I've made an equation that contains the unknown quantity. I want to figure that out, that maximum speed, and everything else is known to us. So then I just had to rearrange the equation. The maximum speed is simply the amplitude of the oscillations multiplied by the square root of k over m. I know the amplitude of the oscillations. I know the spring constant. I know the mass. I can multiply them all together, and I find by doing that, the maximum speed is 0.28 meters per second. And that was quickly solved. That was easily solved. That's the power of this by energy concepts. There's a question in the chat, at maximum speed, wouldn't the potential energy be zero? And the answer is yes. At maximum speed, the potential energy is zero. So I don't want you to get confused about this equation here. It's not saying that the maximum potential energy is at the same moment or instant as the maximum kinetic energy. That's not true. They're at different times. It's saying that the maximum kinetic energy is numerically equal to the maximum potential energy. So the maximum number of joules of kinetic energy that you ever see at any time is equal to the maximum number of joules of potential energy that you see at any particular time. You don't see those two maxima of the potential and kinetic energies at the same time, though. So I hope that makes that a little clearer. Okay, what about the speed when the spring is only partially stretched or compressed, when it's just stretched or compressed 1.5 centimeters? How are we going to figure that out? Well, actually, I figured that out in two kind of steps. My first step, my intermediate step, was to find out the total energy of the mass spring system. And that's actually, we could calculate that one or two ways now. The total energy of the mass spring system is either the maximum potential energy or the maximum kinetic energy. And since we know the amplitude and we know the maximum speed, we could use either of those equations. Once you get the total energy of the spring system, if you know how much the spring is compressed or stretched, you can evaluate how much potential energy it has. The remainder must be kinetic energy. And therefore, if you can find the kinetic energy, you can find the speed. Okay, so let's do that calculation. I'm going to remove this. That shouldn't be that. Okay, so here's my first step. This is really step one. And I'm calculating the total energy of the mass spring system. And as I say, I could do it by equating it to the maximum kinetic energy. I did it here by equating it to the maximum potential energy. That maximum potential energy is half k a squared. And I know the k and I know the a, and so I can multiply them together. The maximum energy of this mass spring system is just 0.0157 joules. At any moment, that total energy is a sum of kinetic energy and potential energy. Now, at the equilibrium point, potential energy is zero. At the fully stretched, fully compressed points, the kinetic energy is zero. But in general, when the spring is partially stretched or compressed, there's a combination of both kinetic and potential energy. And so that's what I'm saying here. At the moment that we're thinking of, when the spring is compressed or stretched 1.5 centimeters, there's both kinetic and potential energy. Well, I can take this equation now and rearrange it for the velocity that I want to figure out when the spring is stretched, compressed 1.5 centimeters. I just rearrange that equation for V. So I take the 1/2 kx squared onto the same side as the energy is on. And then I multiply by 2 and I divide by m and I take the square root. So that's just a bit of algebra. But now if you look at that equation, everything inside that equation, the total energy E, spring constant, the amount that we stretched or compressed the spring, the mass of the object, they're all known to us. We can just plug them in. I won't go through the list of them, but I plug them all in here. We get that speed. We find that, compare this to the 0.28 meters per second. That was the maximum speed. This is a little bit less than the maximum speed. It's a little bit less because you compressed or stretched the spring a little bit. So there's a little bit of potential energy now. And so there's less kinetic energy now. And so you got a little bit less speed now. And so that's, again, a problem where using the ideas of energy conservation, different forms of energy, kinetic and potential, we've been able to solve the problem. Okay, now I've got a few examples of calculations involving different pendulums. And this one's a warm-up exercise. This one's easy, I think. Straightforward, I think. That pendulum I made in the large lecture room in chemistry physics, it had a period, I measured it, it was 3.5 seconds. That's the period for one complete oscillation from the left to the right and back to the left again. So here I am back in chemistry physics. This is a younger me. And I'm watching these oscillations, and I measured it to be 3.5 seconds. Question is, can we figure out the length of the string? And yeah, we can figure out the length of the string, because the characteristic frequency, which means that the characteristic period of the oscillations, is determined by this ratio involving the length of the string and the acceleration of gravity. The longer the string, the longer the period. The shorter the string, the shorter the period. And so I just wrote that down, that the period of the pendulum, which is the inverse of the frequency. So the period is the number of seconds of one complete oscillation. The frequency is the number of oscillations per second. And that frequency itself is the number of radians per second divided by 2 pi. I can then fill in the expression for the angular frequency as in terms of the length of the pendulum and the acceleration of gravity. And so I did that here, and I then rearranged this. I rearranged it and calculated the length. And when I calculate the length, so I've got this expression for the period is 2 pi times the square root of L over G. I squared up the left-hand sides and right-hand sides, and then I multiplied by G, divided by 2 pi squared, and I get this little expression down here. I can fill in the acceleration of gravity on Earth. I can fill in the period. I can fill in the factor 2 pi, and I get a length that is 3 meters. So I had made this pendulum with a 3-meter long cable. And as you see here, the longer the period, the greater the length, or vice versa. The greater the length, the longer the period. Okay, the key characteristic of our simple pendulum, what Galileo noticed and made it useful for time measurements, what we noticed that made it useful for time measurements, is that its period or frequency, period is the inverse of frequency, or frequency is the inverse of period, doesn't depend on the amplitude of the oscillation. So if you remember the little video of the bowling ball, I swung it backwards and forwards at several different amplitudes, but the period was the same. The frequency was the same. Okay. So now I've got a few more examples of pendula that we'll work through in this last 15 minutes or so. So one thing that the pendulum has been used for, one important thing that the pendulum was used for, was measuring the acceleration of gravity. So if you think about that equation for the frequency or the period of the pendulum, it involves the length of the pendulum, something that the pendulum owner would control, the length of the string, and it involves the acceleration of gravity. And so if you know the length of the string, you can measure the acceleration of gravity. And the acceleration of gravity on Earth's surface is kind of interesting. So we always say it's 9.8 meters per second squared. That's sort of true, but it's not exactly true because it does vary. It does vary on the scale of 1%. One reason it varies is that, as I mentioned, Earth has a bulge, and Earth is kind of fatter at the equator than it is at the poles. And it's due to the rotation of the Earth. And that changes the acceleration of gravity as you go from the equation equator to the poles or poles to the equator. Another thing that changes the acceleration of gravity is if you go to the mountains, you know, when there are nearby mountains or valleys, that presence or absence of mass is a presence of absence of additional gravitational forces. That changes the acceleration of gravity. Another thing, and if you are, exploring an oil exploration scientist, right, trying to find oil, there's local changes in gravity due to the density of the rock or the material beneath the Earth's surface. And then finally, another thing that changes the measured acceleration of gravity, if you have a pendulum, is that the moon and the sun are also exerting gravitational forces on us. And so those change the measured acceleration of gravity because they contribute to the acceleration of gravity. Anyway, that was a long story to introduce this problem. In this problem, which is down here, we're told we've got a seconds pendulum. So a seconds pendulum is a pendulum that has kind of convenient length to it for making these sort of measurements of accelerations of gravity. Seconds pendulum doesn't have a period of 1 second. It actually has a period of 2 seconds. 1 second is the interval between passing through the equilibrium point, because every complete cycle you pass through the equilibrium point 2 times. We're told that a seconds pendulum has a length of 0.9927 meters in Tokyo, Japan, and a length of 0.9942 meters in Cambridge, England. So it's slightly shorter in Japan than it is in Cambridge, England. It's a small effect, but the seconds pendulum is slightly shorter in Tokyo than in Cambridge. And that's related to a slightly different acceleration of gravity in Cambridge and Tokyo. And so we're going to calculate the ratio of accelerations of gravity based on the different lengths of the seconds pendulums. So the second, importantly, right, the second is the same length in Tokyo as it is in Cambridge. But the pendulum that you need, the length of the pendulum you need to beat out these seconds, to ring out these seconds, is different in Cambridge and Tokyo, which reflects that the acceleration of gravity is slightly different in Cambridge and Tokyo. Okay, so here's my calculation. My goal is to calculate the ratio of the Cambridge acceleration of gravity to the Tokyo acceleration of gravity. And what I know is the lengths of the Cambridge and Tokyo seconds pendulum. And most importantly, I think what I know is that both these pendula tick out intervals of 1 second. So I should have written 2 here, really, but it doesn't matter. The period of the Cambridge pendulum, the period of the Tokyo pendulum are the same. This is the important thing. Those 2 pendulars' periods are the same. They beat out the same time. Now, this is the expression for the period in terms of the length of the pendulum and the acceleration of gravity. And over here, the same thing for the length of the Tokyo pendulum and the acceleration of gravity in Tokyo. And so, because they beat out the same time intervals, because they have the same periods, I can write down this relationship that contains the accelerations of gravity in the 2 places and the known lengths of the pendula in the 2 places. And then I can just rearrange this, right? The 2 pi's obviously cancel out. I can get rid of the square roots on the left-hand side and right-hand side. And I can rearrange that equation such that the acceleration of gravity in Cambridge compared to the acceleration of gravity in Tokyo, that ratio, is equal to the length of the pendulum in Cambridge divided by the length of the pendulum in Tokyo. And I know those 2 lengths, here they are. And I find that if I take their ratio, then the acceleration of gravity is about 0.15% greater in Cambridge than it is in Tokyo. That's the difference in the gravitational accelerations in those two locations. Anyway, that's an example of working with that characteristic frequency that we figured out for a simple pendulum. And it's also an example of the use of simple pendulum. Because you can measure these time intervals, these durations well, you can use the simple pendulum as a probe of the acceleration of gravity. Okay, I think I'm going to skip this one. I'll solve it and put it as a little example in the modules. But I think the other problem I want to solve is this one, which is kind of an interesting one. It's called the upside down pendulum. I remember taking, when my kids were young, we took them to the upside down house. And I was surprised to see that there was no upside down pendulum in the upside down house. But here's the upside down pendulum. So you can make an upside down pendulum at home. All you need to do is go to Kroger's and you buy a helium balloon with happy birthday written on it. And you tie the string on the helium balloon to the floor. You tape it to the floor. And of course, that pendulum that upside down pendulum with the helium balloon will stand vertically. The ribbon will be vertical. If you displace it to the right, it'll swing backwards through the equilibrium point towards the left, and you made a upside down pendulum. If you displace it towards the left, it will swing back through the equilibrium point towards the right. It will act like an upside down pendulum. And so that's how you build one. And we're told that this one, the length of the string is 3 meters. We're told that piece of information. So this is 3 meters. And we're told the density of air and helium. So the balloon contains helium, which is a very low density gas, 0.18 kilograms per cubic meter. And it's replacing the air that would have been in this region, which has density much larger by comparison to helium. It's 1.29 kilograms per cubic meter. And from that information alone, we're going to calculate the period of our upside down pendulum made with a Kroger's Happy Birthday helium balloon. So let's do that. The first thing is to understand why it's a pendulum, why there's a linear restoring force, and why it will undergo harmonic motion. So that's the key thing, right? So to do that, oops, I almost got to the end of this lecture without doing that with the pen. I was just 2 slides away, and then I went and did it. So that's a little disappointing for me. I'm sketching the forces here. So vertically, this is the equilibrium position. And what I'm sketching is the helium balloon and the string. And specifically, I'm interested in what are the forces on the helium balloon. Well, there's 3 actually. There's an obvious one, which is the weight of the helium balloon. So that's in red, it's acting vertically downwards, it's force of gravity. Probably the next most obvious one is tension. That's in green here, and that's acting along the string. And then thirdly, as we know from last week, the helium balloon is in the air. It's displacing air. There'll be a buoyant force, FB, that's equal by Archimedes' principle to the weight of air that's displaced. And that's trying to lift the pendulum, lift the helium balloon up. And so red, green, and magenta are the three forces that are acting on the pendulum. There's force of gravity on the helium in the pendulum. There's the tension force in the string on the pendulum. And then there's a buoyant force. So those are the three forces that are acting. Now, as we mentioned, right, the key thing about a pendulum or about periodic motion or simple harmonic motion is a restoring force, a linear restoring force. So how does this linear restoring force emerge from the red, the green, the magenta arrows representing these three forces? Well, firstly, the tension does not provide any restoring force because it acts perpendicular right angles to the direction of motion. However, portions of the weight of the helium and portions of the buoyant force from the air, portions of them do act in the direction of motion. So those would contribute to a restoring force. Specifically, right, the air, which is force, which is acting upwards, it's a buoyant force, is trying to a portion of that W sine theta here, where W is the weight of the air displaced, is trying to push the helium back towards the equilibrium point. So that is a restoring force. And then there's a portion of the weight of the helium, so W sine theta, where W here is the weight of the helium, that's trying to actually, it's not a restoring force, it's opposite to that. It's trying to pull the balloon away from the equilibrium point. So there are two contributions. I'll put them in little rectangular brackets here, that act along that direction that the helium balloon can move when it's attached to the string or the cable or the ribbon. And they're the weight of the air times sine theta, which is a restoring force, and the weight of the helium times sine theta, which is opposite a restoring force, an unrestoring force. I don't know what you call an unrestoring force. Based on that picture, I can write down then an equation for the restoring force. And so let me do that. I did that on the next slide. And here it is. So the total restoring force, just called it F, that the helium balloon is experiencing is, well, there's this restoring force due to the displaced air, W sine theta, where W is the weight of the air, and there's this unrestoring force, W sine theta, where this W is the weight of the helium, which is acting in the opposite direction. And if I fill in the masses, the weights in terms of the masses, so use mg. And if I use that small angle approximation again, remember back when I first introduced it, when we were first discussing pendulum, that sine theta is approximately x over L. Then I get this equation here. And we've discovered that this upside down pendulum does have a linear restoring force. The force on the left here is in proportion to the inverse proportion. There's a minus sign here. Sorry, is in proportion to the displacement, is in the opposite direction to the displacement. So that is a linear restoring force. So we found our linear restoring force. So that's like a, I think of that as a little hide and seek. We sort of worked our way through the forces, and we found inside all those forces, thinking about tension, thinking about weight of the air, thinking about weight of the helium, we found the linear restoring force. Now we've found the linear restoring force, I can find the characteristic frequency. Remember, all you have to do to find the characteristic frequency is write down the corresponding equation for the acceleration. It's this one here. You just divide through by the mass of the object, the mass of the helium. And the coefficient between the acceleration on the left and the displacement on the right, that coefficient we've learned to recognize is the square of the characteristic frequency of the, in this case, upside down pendulum, the thing that's going to undergo periodic motion because of the linear restoring force. Well, now our job is almost done. Last slide. Now we've got an equation for the characteristic frequency, the characteristic angular frequency. It's this one here. I can rewrite it. I rewrote it, instead of in terms of the masses of air and helium, I divided by the volume of the balloon and wrote it in terms of the densities of the air and the helium, because we were told the densities of the air and the helium. But this equation here contains everything we know, right? It contains the densities of the two gases, the length of the string, and the acceleration of gravity. All I have to do is plug in those numbers. I get the angular frequencies, 4.5 radians per second. And if I invert it and multiply by 2 pi, that's the period. The period is 1.5 seconds of this upside down pendulum. And so that's our final example of periodic motion. Well, let me end there. Next class, we're going to just do a little review of material for the tests.